All right, so let's dive into something that's both
Nice.
iconic and maybe a little intimidating, right?
Yeah.
The periodic table.
Right.
Yeah, I've all seen it, that colorful grid, hanging in a classrooms, maybe on a t-shirt or two.
Hmm.
But let's be honest, how much do we really understand about what's going on
Yeah.
in that masterpiece of organization?
That's a good question.
That's what we're here to uncover today.
Yeah.
The logic behind the layout,
Mm-hmm.
the surprising trends hidden within the rows and columns,
Absolutely.
and our guide for this deep dive.
Yeah.
Excerpts from the Wikipedia article on the periodic table itself.
Oh, wow.
You might be surprised
Okay.
how fascinating it gets.
It truly is fascinating. I think the periodic table isn't just a random chart
Yeah.
of elements. It's like a giant puzzle where each element fits in a very specific way
Right.
based on its properties.
Okay.
And those properties,
Mhm.
they're determined by the way those tiny little electrons are arranged
Wow.
within an atom.
Okay, so before we get lost in the electron clouds,
Okay,
let's start with the basics.
sure.
What exactly is the periodic table trying to do?
Okay.
What's its purpose?
The periodic table's purpose is to organize all the known chemical elements in a way that reveals their relationships
Okay.
and helps us predict their behavior.
Got it.
Now, you might think they're arranged by weight,
Oh, yeah. I could see that.
but that's actually how some early versions were organized.
Really?
The modern periodic table is arranged by atomic number,
Okay.
which is the number of protons
Right.
in an atom's nucleus.
Okay, so each element gets its own little box on the table based on how many protons it has.
Yes.
But it's not just a jumbled list of numbers, right?
Yeah, no.
There's a structure here
Yes, there is.
with rows and columns.
Exactly. Those rows are called periods and the columns are called groups.
Okay.
And here's the cool part. As you move across a period or down a group, you see trends
Mm-hmm.
in the element's properties.
Oh, interesting.
Like a pattern repeating itself,
Okay.
which brings us to the periodic law.
Ooh, a law of chemistry.
Yes. The periodic law states that the properties of elements repeat in a predictable way as you move across those periods.
Okay.
Think of it like waves on the ocean.
Okay.
They rise and fall in a regular pattern.
Yeah.
So you might see a property, like
Mhm.
how easily an atom loses an electron,
Go.
increase as you move across a row, then drop at the start of the next row.
Right.
And the pattern continues.
Okay.
It's this repeating pattern that gives the table its name, periodic.
So I'm starting to see the logic here,
Yeah,
but there's more to the table than just rows and columns.
right.
We've got those colored blocks too, the S block, P block, D block, and F block.
Yes.
What's the deal with those?
Those blocks aren't just for decoration. They actually correspond to something called electron configuration,
Okay.
which is basically a map of where electrons live in an atom.
Okay. Electron configuration. That sounds a little intimidating.
Yeah.
But it can't be that bad, right?
It's simpler than it sounds.
Okay, good.
You see, electrons aren't just randomly buzzing around an atom.
Right.
They're organized into different energy levels called shells,
Okay.
kind of like layers in an onion.
Okay, I like that analogy.
Within each shell,
Yeah.
there are subshells,
Okay,
and each subshell can hold a certain number of electrons.
got it.
The S, P, D, and F blocks on the periodic table represent which type of subshell is being filled as you add electrons to an atom.
Okay, so if I'm looking at an element in the P block,
Yes.
I know its electrons are filling up a P subshell.
You got it. And here's why this is so important.
Okay.
Electron configuration is the key to understanding all those trends
Right.
you see in the periodic table.
Right.
It's like a blueprint that tells us how an element will behave based on how its electrons are arranged.
Okay, I'm starting to see the connection
Yeah.
between where an element sits on the table and how it acts in the real world. So let's dive into some of these trends. What kind of properties are we talking about?
There are several key trends,
Okay.
but let's start with atomic radius.
Okay.
Basically how big an atom is.
I always pictured atoms as being tiny and all roughly the same size.
Right.
Is that wrong?
Definitely not. Atoms come in different sizes,
Okay.
and the general trend is that atomic radius decreases
Okay.
as you move across a period left to right, and increases as you move down a group.
Got it.
But here's a curveball. That very first row with elements like hydrogen and helium is weirdly small.
Why are they so tiny?
Imagine this. Think of electrons like tenants living in an apartment.
Okay.
In the first row, it's like they're crammed into a studio apartment. Not much space to spread out. making the radius of the apartment small as you move down the periodic table.
Okay.
It's like moving to larger apartments with more rooms.
Okay.
The electrons have more space,
Got it.
so the atomic radius gets bigger.
That's a great analogy.
Thank you.
Okay, so atoms get bigger as you go down a group. But what about those other trends?
Another key trend is ionization energy,
Okay.
which is basically a measure of how much energy it takes to rip an electron away from an atom.
Well, sounds kind of rough for the atom.
It is a bit dramatic,
Yeah.
but it's an important concept.
Okay.
And the trend for ionization energy is the opposite of atomic radius.
Uh-huh.
It increases as you move across a period
Okay.
and decreases as you move down a group.
Okay.
But just like with atomic radius, we have an exception. Oxygen doesn't quite follow the rules.
What's going on with oxygen? Why is it so rebellious?
It comes down to how its electrons are paired up in that apartment.
Okay.
It's like two electrons are sharing a room and maybe not getting along so well.
Right.
So it's a bit easier to evict one of those electrons than you'd expect based on the general trend.
So its ionization energy is lower
Yes.
than its neighbors.
Lower than its neighbors.
Interesting. So those tiny electron pairings can have a big impact on an element's properties.
Absolutely. And that brings us to another property influenced by these pairings, electronegativity. Think of it as how strongly an atom clings to electrons when it's sharing them with another atom in a bond.
So some atoms are like electron hogs.
Exactly.
They just want to hold on tight to all the electrons.
And the trend for electronegativity is similar to ionization energy.
Uh-huh.
It increases across a period and decreases down a group.
And this is all still connected back to electron configuration, right? The arrangement of those little guys determines how greedy an atom is for electrons.
Precisely. It all comes back to those electron arrangements.
Okay.
But there's one more term I bet you've heard and wondered about.
Okay.
Metallicity.
Okay, yeah.
I know it has something to do with metals, but what does it really mean?
I'll admit, metallicity always sounded a bit vague to me.
Yeah.
I get that it's related to metals, but beyond that, it's kind of a mystery.
Metallicity isn't just about whether something is shiny or conducts electricity.
Yeah.
It's about how freely the electrons can move around.
Right.
Remember that sea of electrons we talked about with atomic radius?
Right.
That's a hallmark of metallic bonding.
Right. The bigger the apartment, the more freely those electrons can roam around.
Exactly.
So metallicity is tied to how easily those electrons can flow.
Exactly. And guess what? We can link this back to electron configuration, too.
Oh, wow.
Metals tend to have those outer electrons loosely held,
Okay.
which allows them to delocalize,
Right.
forming that sea of electrons that gives metals their characteristic properties.
Uh-huh.
Nonmetals, on the other hand, hold on to their electrons more tightly.
Okay. I'm really starting to see how all these pieces fit together.
Mm-hmm.
The periodic table isn't just a random chart. It's like a map of the elements,
Yeah.
where their position reveals their secrets.
Yes.
But I've also heard that the periodic table isn't without its quirks,
Right.
like debates about where certain elements belong.
You're right. There are definitely some head scratchers.
Okay.
Take hydrogen and helium, for instance.
Okay.
Based on their electron configurations, they should technically be in groups 1 and 2,
Right.
but you usually see helium hanging out with the noble gases.
Yeah. What's up with that?
Way over in group 18.
Why is helium hanging out with the cool kids? It seems like it should be with its electron configuration buddies.
It's a tug of war between where its electrons say it should be and how it actually behaves.
Right.
Helium acts a lot like the other noble gases.
Okay.
Very unreactive,
Yeah.
kind of aloof, even though its electron configuration aligns more with the alkali metals.
So sometimes an element's behavior trumps its electron configuration.
Yeah, it's more like a balancing act.
Okay.
We try to consider both factors when organizing the table, and
Right.
sometimes that leads to these interesting placement debates.
Yeah. Okay.
And it's not just individual elements.
No.
There are even debates about larger chunks of the table,
Oh, really?
like the whole group 3 problem.
Group 3 problem. Okay, now I'm really intrigued.
Yeah.
Tell me more.
So, welcome back. Let's unravel this group 3 problem.
Okay.
You see, there's a whole section of elements called
Right.
the F block, which includes those tongue-twisting lanthanides and actinides.
Yeah, those are tough.
They're usually shown as separate rows below the main table, kind of like footnotes.
Right.
But technically, they belong somewhere in group 3.
Oh, really?
The question is where exactly. It's like trying to squeeze an extra guest into a dinner party that's already perfectly arranged.
Ah, so even though the periodic table seems so neat and tidy,
Right.
there's still room for debate and interpretation.
Absolutely. And as we discover more elements, especially those super heavy ones at the edge of the table, we might need to rethink our understanding of the periodic table even further.
Wow.
It's a dynamic, ever-evolving puzzle.
Speaking of super heavy elements, you mentioned something about relativistic effects earlier.
Yes.
It sounds like Einstein is messing with the periodic table.
It's not that far off. When you get to those super heavy elements, the electrons are zipping around the nucleus so fast that Einstein's theory of relativity actually comes into play.
Real.
And that can have some really bizarre effects on an element's properties.
Hold on. Relativity. Like the theory that says time and space are relative.
Yes.
I didn't know that had anything to do with chemistry.
It's wild, right? But at those super high speeds, electrons start acting a bit differently than we'd expect based on classical physics.
Oh, wow.
For example, remember how we talked about mercury being a liquid at room temperature?
Yeah, it's always seemed strange that a metal could be a liquid.
Well, guess what? That liquid state is actually due to relativistic effects. The way those speedy electrons behave in Mercury's atoms actually lowers its melting point, making it liquid at temperatures where other metals would be solid.
That's so weird.
And as we get to even heavier elements, those relativistic effects become even more prominent, even changing an element's color.
Oh, wow.
Or how it reacts with other elements.
Okay, this is blowing my mind a little bit.
Yeah.
So Einstein's theory is partly why we can use mercury in thermometers. Who knew?
It's all connected, and that's what makes the periodic table so fascinating.
Right.
It's not just a static chart on the wall. It's a dynamic map of the elements full of surprising trends, exceptions, and even mysteries that we're still unraveling.
This deep dive is already making me see the periodic table in a whole new light.
That's great.
It's like a detective story
where
we're using clues from electron configuration and those mind-boggling relativistic effects to understand how the elements behave. But before we get too lost in the mysteries of the super heavy elements, let's go back to some of the trends we were discussing. You mentioned ionization energy. Electronegativity.
Yes.
How do those properties actually play out in the real world?
Well, consider the halogens, those elements over in group 17. We've got fluorine, chlorine, bromine. You might recognize them from things like toothpaste or swimming pools.
Ah, the halogens. Oh, are they known for being pretty reactive?
Yes.
Like they really want to bond with other elements?
Exactly. And we can understand their reactivity by looking at their electron configuration. They're all just one electron shy of having a full outer shell. Making them very eager to grab an electron from another atom to complete their set. Imagine them playing a frantic game of musical chairs, desperate to find an open seat.
So their position in that second-to-last column makes them predisposed to react with other elements to fill that electron vacancy.
Precisely. And this reactivity actually decreases as you move down the group.
Interesting.
Fluorine at the top is the most reactive of the bunch. While iodine further down is a bit more chill. Remember how atomic radius increases as you go down a group? The outer electrons in iodine are farther away from the nucleus, making them less tightly held and less desperate to snag an extra electron.
So it's like the bigger the atom, the less intensely it needs to grab another electron.
Exactly. And this ties directly into electronegativity, remember? The strength of that electron grabbing power, fluorine being small, and with those outer electrons close to the nucleus, is super electronegative, while iodine is less so.
This is making those trends so much clearer. It's not just some abstract concept. It explains why certain elements behave the way they do in real-world situations.
Exactly.
But it's not just reactivity, right? What about other properties, like melting point?
Melting point is another great example. Consider the alkali metals in group 1. Lithium, sodium, potassium. You might have seen videos of them reacting explosively with water.
Oh, yeah, those videos are wild.
Yes.
But they don't look like typical metals. They're kind of soft and well-melty.
Exactly. And that's because they have very low melting points.
Interesting.
They're so soft, you can cut them with a knife.
Wow.
This goes back to their electron configuration and that sea of electrons we talked about.
Yeah.
They have just one outer electron that's very loosely held.
Okay.
Which is great for forming that sea and conducting electricity. But it also means the bonds between atoms are relatively weak, resulting in those low melting points.
So the way the periodic table is organized allows us to make predictions about the physical properties of elements, too.
Right.
Not just their chemical reactivity.
Precisely. And get this.
Yeah.
These trends apply even to elements that haven't been discovered yet. Scientists can use the periodic table to predict the properties of hypothetical elements.
Really?
Guiding their search for new additions to the table.
That's incredible. It's like the periodic table is a treasure map to the unknown elements, giving us clues about what to look for and how they might behave.
That's why the periodic table is considered such a fundamental tool in chemistry.
Okay.
It's not just a chart.
Right.
It's a predictive tool that helps us make sense of the vast and intricate world of elements.
So are we saying that scientists could theoretically predict the properties of an element that hasn't even been discovered yet?
Right.
Just by looking at its potential place on the periodic table?
Exactly.
Could they say,
yes,
okay, if we could create element 125, it would probably be a silvery white metal with a really high melting point because of where it would sit on the table.
You're getting it.
Yeah.
That's exactly what makes the periodic table so powerful. It's like having a sneak peek into the nature of matter itself.
Yeah.
And sometimes those predictions lead to the discovery of brand new elements that fit right into the gaps of the periodic table, further validating its structure and elegance.
Okay, my mind is officially blown.
Good.
This deep dive has taken the periodic table from a colorful chart I vaguely remembered from school to a dynamic predictive tool that's still evolving and shaping how we understand the elements.
Right.
But I have a feeling there's even more to uncover.
You're absolutely right.
Right.
We've talked about structure, trends, quirks, but there's a whole historical side to the periodic table that's just as fascinating.
Now that you mention it, I am curious about the history.
Yeah.
I mean, this table didn't just magically appear one day, right?
Definitely not. The periodic table as we know it today is the result of centuries of scientific inquiry, trial and error, and some truly brilliant minds.
Yeah.
It's a testament to the human desire to understand the building blocks of our universe.
This is making me think about those scientists who were working on these ideas before we even knew about protons, neutrons, electrons.
Right.
They were essentially working in the dark.
It's true.
I can't even imagine trying to organize the elements without knowing about atomic structure.
It's remarkable, isn't it?
Yeah.
Early attempts to classify elements were based on observable properties.
Okay.
Things like reactivity appearance, whether they were gases, liquids, or solids at room temperature.
Right.
But things really started to come together in the mid-1800s, and there's one name that always comes to mind.
Okay.
Dmitri Mendeleev.
Mendeleev. He's the one who usually gets the credit for creating the periodic table.
Exactly. And what's incredible is that he did it before we knew about the structure of the atom.
Really?
He was working purely with atomic weights and the properties of the known elements.
So how did he manage to create this incredibly insightful tool without the fundamental knowledge of what atoms are made of? It seems impossible.
It really is remarkable. Mendeleev meticulously arranged the elements by atomic weight. And in doing so, he noticed that certain properties, like how they reacted with other elements, their melting points, even their densities, repeated periodically.
Wow.
It was like a hidden pattern was emerging from the chaos.
So he saw the trends
Yes.
before we even understood the underlying reasons why those trends existed.
Exactly. And he was so confident in the power of this pattern that he even left gaps in his table.
Oh, really?
Predicting the existence of elements that hadn't been discovered yet.
Wow. Okay.
He even went so far as to predict the properties of these missing elements based on their position within his table.
Well, he was basically saying there should be an element here with these properties, even though we haven't found it yet. That's some serious scientific intuition.
It was a bold move, and it turned out to be a stroke of genius.
Right.
Elements like gallium and germanium were discovered later, and their properties matched Mendeleev's predictions almost perfectly.
Wow.
It was a huge triumph for the periodic law and cemented the periodic table's place as one of the most important tools in the history of science.
So Mendeleev's version was organized by atomic weight.
Yeah.
But our modern periodic table is organized by atomic number.
Right.
What prompted that shift? When did we finally figure out what was really going on inside those atoms?
That shift came in the early 20th century with the discovery of the atom's structure.
Okay.
Scientists like Ernest Rutherford and Henry Moseley figured out that the number of protons in an atom's nucleus, its atomic number, was the true key to its identity.
Wow.
It's like we finally cracked the code that unlocked the deepest secrets of the elements.
Right.
And that's when the modern periodic table, organized by atomic number, was born.
It's amazing how each scientific breakthrough, like understanding atomic structure, refined our understanding of the periodic table. It's like we were building this incredible tool piece by piece, layer by layer, without even knowing the final blueprint.
And it's a process that continues to this day. Even now, as we push the boundaries of our knowledge and create new super heavy elements, the periodic table is evolving.
Okay, I'm ready to dive even deeper into this history. Take us back to the beginning, to those early attempts to classify the elements. What were some of the ideas that came before Mendeleev's breakthrough?
Well, before Mendeleev, chemists were trying to make sense of the elements based on their observable properties. One early attempt was to group them into triads.
Triads, like groups of three.
Exactly. Johann Dubereiner, a German chemist, noticed that certain groups of three elements had similar properties. And the atomic weight of the middle element was roughly the average of the other two.
Oh, wow.
For example, lithium, sodium, and potassium, all soft reactive metals, formed a triad.
So it was like a mini version of the periodic table, but just with three elements at a time.
Exactly. It was a step in the right direction, but it didn't quite capture the full picture. Another interesting approach was the telluric helix, developed by Alexandre-Émile Béguier de Chancourtois.
A telluric helix. That sounds complicated.
It was a visual representation of the elements arranged in a spiral around a cylinder.
Oh, wow.
De Chancourtois noticed that elements with similar properties appeared at regular intervals along the spiral.
Interesting.
It was like a three-dimensional precursor to the periodic table.
So even back then, they were trying to find visual ways to represent the relationships between the elements. It's like they knew there was a pattern hidden there just waiting to be discovered.
Exactly. These early attempts, while not perfect, laid the groundwork for Mendeleev's breakthrough. They demonstrated that there was a deeper order to the elements waiting to be revealed.
This is giving me a whole new appreciation for the history of chemistry.
Yeah.
It wasn't just one aha moment.
Right.
It was a gradual process of observation, experimentation, and building upon the work of others. It's like a relay race, with each scientist passing the baton to the next generation.
That's a great way to put it. And that relay race is still going on today.
Wow.
With the discovery of new elements and the development of new theories, the periodic table continues to evolve and challenge our understanding of the universe.
So to our listener, we're taking a break here, but we'll be back in part 3 to explore more about the modern periodic table and how it continues to shape our understanding of chemistry, physics, and even the cosmos. Welcome back to our deep dive into the periodic table. It's amazing how much ground we've covered, from the basics of atomic structure to those mind-boggling relativistic effects we've seen, how the periodic table evolved, from early attempts to classify elements into the sophisticated tool we use today. But I have a feeling there's even more to this story.
You're right, there's always more to discover. We've talked about the historical development, but what really makes the periodic table so powerful is its ability to not only organize what we know, but also predict what we don't know.
You mean like predicting the properties of undiscovered elements? We touched on that briefly, but it's such a fascinating concept. How is that even possible?
It all comes down to those trends we've been discussing: atomic radius ionization, energy, electronegativity. These trends aren't random. They're based on the underlying principles of atomic structure and how electrons behave. So if you know where an element should sit on the periodic table based on its atomic number, you can make some pretty educated guesses about its properties.
So it's like having a cheat sheet for the universe. You could look at the periodic table and say, okay, element 118 should be a noble gas because it falls in that last column, with all the other unreactive gases.
That's a great way to put it. Of course, it's not always that straightforward, especially when you get to those super heavy elements where relativistic effects can really throw a wrench in the works. But even then, the periodic table gives us a framework for understanding how those elements might behave.
So how do scientists actually go about discovering these new elements? Are they just smashing atoms together and seeing what happens?
It's a bit more complicated than that, but smashing atoms is definitely part of the process. It involves using particle accelerators to fire beams of atoms at incredibly high speeds at a target. When those atoms collide, they can sometimes fuse together, creating new, heavier elements.
So it's like a microscopic game of billiards with atoms as the balls.
That's a good analogy, but it's an incredibly difficult and delicate process. These super heavy elements are often extremely unstable, existing for only fractions of a second before decaying into lighter elements.
It sounds like trying to catch a snowflake on your tongue before it melts. So how do scientists even know they've created a new element if it disappears so quickly?
They look for the telltale signs of its decay. When a super heavy element decays, it releases specific particles and energy that scientists can detect. It's like piecing together a puzzle, using those decay products to figure out what the original element must have been.
It sounds like detective work on an atomic scale.
It is. And each new element we discover adds another piece to the puzzle of the periodic table, pushing the boundaries of our understanding of matter and the forces that govern the universe.
This is making me think about those gaps in Mendeley's original table. Those elements he predicted before they were actually found. It must have been incredible for scientists to finally discover those missing elements and see that they fit perfectly into his framework.
Absolutely. It was a validation of the predictive power of the periodic table, and even today, that predictive power continues to guide the search for new elements. It's like having a map that tells you where to look for buried treasure.
So where are we at today? What's the latest in the search for new elements?
Well, the heaviest element officially recognized by the International Union of Pure and Applied Chemistry is oganesson element 118. It was first synthesized in 2002 and is named after Yuri Oganesyan, a Russian physicist who played a key role in its discovery.
Oganesson element 118, it sounds almost mythical.
It really is. But scientists are already on the hunt for elements beyond oganesson elements 119, 120, and beyond these elements are predicted to be even more exotic and unstable, pushing the limits of what we thought was possible in terms of atomic structure.
It's like we're entering a whole new realm of chemistry, a realm where the familiar rules might not always apply.
Exactly. And as we venture deeper into the realm of super heavy elements, the periodic table will continue to evolve and adapt, guiding us as we navigate this uncharted territory.
This deep dive has really opened my eyes to the power and beauty of the periodic table. It's not just a chart of elements, it's a testament to human ingenuity, our relentless curiosity about the universe, and our ability to uncover hidden patterns and connections in the world around us.
And it's a reminder that there's always more to learn, more to discover. The periodic table is a living document, a work in progress that will continue to evolve as we expand our knowledge of the universe.
So to our listener, we encourage you to keep exploring the periodic table. Delve into the stories behind the elements and marvel at the intricate connections that weave this tapestry of matter. Who knows what amazing discoveries await us as we continue our journey into the heart of the atom.
And perhaps one day you'll be the one to discover a new element, adding your own chapter to the ever-unfolding story of the periodic table.